Hey, welcome back, mathematicians. Today we're going to talk about graphing exponential functions. These are not going to be super hard, I hope, for us. And of course, my pen's broken. I hope they're not going to be too bad for us because mostly what we're going to be doing today is describing the transformations of the graph from the parent function based on the equation and by looking at the graph. Honestly, it's not even going to be a transformation. It's going to be just the key features like intercepts, increasing, decreasing, end behavior, domain, range, things like that. So let's start by talking about what an exponential function is going to look like and some of the weird properties that they have, and then we'll go look at some examples together. So for the key features of a exponential function, you want to know in general if they are growth or decay. So growth graphs are going to look kind of like this blurry thing here. What's going to happen is on one side, they're going to taper off and get really small. And on the other side, they're going to curve upwards and start growing really quickly. Exponential decay is kind of the opposite. They start large and then they decay or taper off as they go the other direction. So our growth graph is going to increase as the x increases. These are what are called monotonically increasing or decreasing, meaning they either always increase or always decrease. So the increasing, decreasing, if they ask us about that, will be very easy. And then decay functions always decrease or decay. All exponential functions without shifts will have a y-intercept at 0, 1. So right here is 0, 1. Right here is 0, 1. That's growth and decay functions have the same y-intercept. If it gets shifted up or down, so let's say it has like a little +3 on the end, so this thing goes up 3, then obviously it's not going to have the same y-intercept. But if we don't move it around, all exponentials, regardless of their base, so it could be y equals 2 to the power of x, y equals -1/3 to the power of x, anything will always have the same y-intercept. And they're going to have this thing called an asymptote at y equals 0. So we're going to talk about what asymptotes are on the next slide. Right here. So what an asymptote is, and be careful how you say this, otherwise your mom's going to get mad and she's going to be like, hey, don't cuss in my house, otherwise I'm going to slap you with a sandal. All exponential growth and decay graphs have asymptotes, and asymptotes are a line that the graph continually approaches. This says it maybe a little backwards from the way that I think about it. This says an asymptote is a line that continually approaches a given curve. I think about it as the curve getting closer to the line. It's like an invisible line that your graph is going to try and get really, really close to, at least on one side. Another handy way to think about asymptotes is as a boundary line that tells you where your function, it doesn't actually stop, but we say that it approaches it, or it keeps getting closer and closer and closer to that point. This asymptote is not only a key feature you'll need to identify, it's also it will also alter the way we find end behavior. It's going to make finding end behavior very easy for us when looking at key features of the graph. So again, if we don't have a vertical shift, it's going to be y equals 0 for our asymptote. This is the equation of a line. Y equals 0 is this line right here. It's the x-axis. If we have a vertical shift, then our asymptote is going to be y equals k, or whatever the vertical shift is. So if k is 2, then we're going to have a vertical line up here at 2. And typically we draw asymptotes with a dashed line because usually they're invisible. You don't graph them unless someone tells you to. So to help us just guide the drawing of our regular graph, usually we put a dashed line to show, hey, here's an asymptote. It's invisible, but I need to look at it to be able to draw my graph. All right, let's go look at some examples. So here's a graph. This is exponential growth because we can see as it goes to the right, the value increases. And here is the function of this exponential growth equation. Let me point out a couple of important values to you that will help us find this stuff, and then we'll look at it. So for any exponential growth function, you're going to have some base to the power of x minus h plus k. K is what we talked about back here. K is your vertical shift, and it's going to tell us where our asymptote is. So if we look at what number is being added or subtracted to the thing with the exponential on it, that'll tell us our asymptote. This h will also tell us the horizontal shift, but I don't necessarily think this is going to be very important in this lesson, but good to know. So let's look at our intercepts. This doesn't say x-intercept or y-intercept, so we'll just assume it means both x and y-intercepts. So where does it touch the x and y-axis? We can see that this is never going to touch the x-axis. It's down here, and it looks like this graph kind of just tapers off and stays steady at 3, if I could draw a straight line. Stays steady at 3 right there. This is actually our asymptote. So let's go ahead and fill that out. We can see k is 3 right there. So our asymptote is y equals 3. It's this invisible red line that I drew that our graph is going to gradually taper towards. For our intercepts, we can see right here, it crosses the y-axis. This looks like 0, 3.5. And we could check this. The way you check for a y-intercept is you plug 0 in for x into your equation and then simplify. So if we do that for ours, it'll be 2 to the power of 0 minus 1 plus 3. 0 minus 1 is negative 1. So we have 2 to the negative 1 plus 3. And 2 to the negative 1 is the same as 1/2. So 1/2 plus 3 is 3.5. And we can see our intercept. That's our only intercept. It will never touch the x-axis. The domain for exponential functions is very easy because it's the same for every single exponential function. It is all real numbers. And we could write all real numbers with the symbol for all real numbers, which is just the double R. Or we could write it in interval notation. So parenthesis, negative infinity to infinity. Any of these 3 ways of writing it would be acceptable. I'm not sure what you're going to see on your homework, but it's probably multiple choice, and you just pick the one that they give you. Okay. The range is a little bit harder. In general, for exponential growth and decay functions, your range is going to be from the asymptote number to infinity. The reason the asymptote number gets a parenthesis instead of a bracket like this, it's not that. The reason it gets that is because by definition, an asymptote is a line that the graph approaches but never touches. It's like what's the vulgar word that you can kind of like hear when you say asymptote? Would you walk around the store just grabbing people's asymptotes? Probably not. You can't just walk around and slap people's booty cheeks. So same thing here. Functions can't go slap booty cheeks either. So they get really close, but they never quite touch because they're polite young men and women and non-denominationals. And they don't sexually assault people. So, all right. So our range is 3 to infinity, parentheses on both of them, parentheses here because of the asymptote, parentheses here because you can never get to infinity. For the end behavior, this is either going to be infinity or the value of your asymptote. So you just have to know which side to put it on. So as x goes to negative infinity, this is saying the left side. On the left side of our graph, does this thing curve up and go to infinity, or does it get closer and closer to 3? Well, I'm hoping you guys can count 1, 2, 3. So this one, whoops, they're connected, is going to go here. So f of x goes to 3. As x goes to infinity, so as we go to the right really far, what happens to this? The farther right this goes, the more up it goes, up to infinity. Okay, so there we go. We have all the key features of this graph. Pretty easy. Let's go look at another one. All right, so here we can see that we have a couple of intercepts. We can see that our graph crosses the x-axis right there, and the ordered pair there is -2, 0. That's an x-intercept. And we can see that our graph crosses right here. That's a y-intercept, and that's going to be 0, 6. Again, to find these, we could do some algebra on this, but it's probably not necessary. You can just look at it. It's pretty straightforward visually as long as you have the graph. For our asymptote, we can just look at this right here. This is our k value. So our asymptote is going to be y equals k, so -2. Our domain is always all real numbers, so -infinity to infinity. Our range goes from the asymptote value, -2 to infinity. And then our end behavior, as x goes to the left forever, to -infinity. Is it going up or is it going to -2? Well, it looks like it's going to -2. As it goes to the right, it curves up and increases forever to infinity. Well, not too bad. When you're taking your notes, you don't need to draw this whole graph, right? I think it's important that you get maybe this, get an axis, maybe go 1, 2, put a point, 1, 2, 3, 4, 5, 6, put a point, and then maybe like a little line here at -2 and just draw like that. It doesn't have to be perfect. You can just sketch them. I understand that taking notes on graphs can be a little challenging just because you want to get them perfect. If you want them perfect, I recommend you just beg and plead with your parent to buy you graph paper. It'll change your life. It's seriously the best thing ever to have in a math class. All right, let's do one more here. This one, our intercept, we can see that there's this y-intercept, and then it curves down towards this invisible asymptote. So it's never going to touch the x-axis. So no x-intercepts, but we have a y-intercept here. This is halfway between 4 and 6, so we're going to say that that's 5. Every 2 of these little lines is 1. So our y-intercept is at 0, 5. Our asymptote is y equals whatever this number is, so 4. Our domain for every single exponential is all real numbers. Our range always goes from our asymptote to infinity, parentheses on both sides. Then our end behavior. This one's a little bit different than the other two we've looked at. As x goes to -infinity, if we look at the left side, this is an exponential decay graph, so the left side goes up and the right side tapers down towards the asymptote. So as we go left, this points up, so it's going to go to infinity. As x goes to infinity, as we go to the right, this graph tapers towards the asymptote. The asymptote's at 4, so the end behavior goes towards 4. All right. Now let's talk about u-graphing some. You're going to have to identify graphs on your homework. They're going to give you an equation, and you're going to have to pick the graph that matches it. The easiest way to do that is get a graphing calculator. And here's the link to Desmos. You obviously can't click on it because it's a video. Maybe I'll put it in the description. I don't know. It'll probably be embedded in your homework anyway. Don't worry about it. So I would just grab a graphing calculator. I'm going to sort of show you how to graph stuff by hand, but as far as your homework goes, it's going to be much, 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 much easier for you to type it in, look at a picture of it, and then try and match it to the pictures you're being shown on your homework. All right, so we have two of these. We want to graph these two functions. Okay. The first thing I can do for both functions is put my asymptote on at these k values. So this one's going to be at 1. Let me actually get a nice line making tool instead of some kind of janky hand-drawn one. So we're going to be at positive 1. Positive 1 is going to be halfway between 0 and 2, so it's going to be up 2 lines. So there's our asymptote. One side of our graph is either going to, or one side of our graph is going to follow it, and then the other side will curve away. So it'll look generally kind of like one of these two graphs. Okay. Here, our asymptote is at -2, so we can just go ahead and put a dashed line at -2 for our asymptote. All right, now we have to find some ordered pairs to plug into our graph. The way I recommend you do that is just make an XY table and plug in a few different values. For X, what I would do here is solve this for 0. Say this equals 0. So X minus 2 equals 0, add 2. So X equals 2. I would pick that as your middle number. So 2, and then go +1, +1, -1, -1. Same thing here. Set this equal to 0, and then solve for X. So we get X equals -3. Make that your middle number, -3. Then +1, +1, -1, -1. And then that will help you get a pretty good idea of your graph. So we can just go ahead and plug these in. If we plug in 2 to this, 2 minus 2 is 0. So we're going to have 3 to the power of 0 plus 1. 3 to the power of 0 is 1, plus 1 is 2. So when we're at, what number do we plug in? 2, we're going to be at 2. Okay. Then you can plug in some other values. Maybe plug in 0 might be another good one, so we could get the y-intercept. So if we plug in 0, we're going to get 0 minus 2. We're going to get 3 to the -2 power plus 1. 3 to the -2 power is 1 over 3 squared plus 1. 1 over 3 squared. 3 squared is 9. So this is 1 over 9 plus 1. So it's 1 and 1/9. It's going to be real small like that. And then maybe one more. Let's get a bigger number. Let's try 4 maybe. If we plug in 4, you're going to have 4 minus 2 is 2. So we're going to have 3 squared plus 1. 3 squared is 9 plus 1 is going to be 10. So you're going to be 4, 10. Here's 2, 4, 6, 8, 10. It'll be way up there. So our graph is going to look something kind of like that. Because it's exponential growth, we know that the left side is going to taper towards the asymptote and the right side is going to increase forever. And that's pretty much the idea. We can tell the general shape of this already. Because it's exponential decay, it's going to do something like this. Okay. But let me show you maybe some tricks. So in general, your y-intercept will be 1 above your asymptote and then shifted however. So our graph is going to look probably something like this. Okay. But here's our h value. Remember, h does the opposite. So this says plus 3, so we would want to go minus 3 or left 3. So if I just take this whole graph and go 1, 2, 3, that's probably pretty stinking close to what it would look like if I plugged in numbers. And we could plug in some numbers really fast. If we plug in -3, we'll get 0, of course. Anything to the power of 0 is 1. So 1 minus 2 is -1. So at -3, we'll be at -1. Oh, look, hey, that's my point that I just guessed. If we plug in 3, this will be 0. So if we plug in 3 right here, 1/2 to the power of 0 is 1. Minus 2 is -1. So at 3, we'll be at -1. Did I goof this up? Maybe that should be there. No. I think I goofed something up. Oh, sorry. I'm doing this wrong. If I plug in 3, 3 plus 3 is 6. We did the -3. If we plug in 0, 0 plus 3 would be 3. And then we have 1/2 to the third power minus 2. This will be 1/8 minus 2. So this is going to be -1 and 7/8. So -1 and almost down there. Okay. So that's kind of a gist of how you do it. You can either plug in x's, like I did over here, just to get an idea. But honestly, your best bet for doing your homework, doing it accurately, is going to be by putting it into Desmos or some other graphing utility. So go ahead and try that. Close this, go to open your homework, try the problems. If you're getting stuck, say, hey, Mr. Barton, I'm getting stuck. Can you help me figure out which graph it is? And then I'll graph it on Desmos, and then we can look at the options together, and I'll help you figure out which one you're looking for. So I hope this video has been educational, maybe even inspirational for you. If not, then oh well. I don't care. But if it has, I'm glad I've helped. Otherwise, have a wonderful day. Make sure you like and subscribe. How about we just like? I'm not gonna get greedy. How about you just like the video? That'd be cool. I want to see my engagement numbers go up. But if you want to subscribe or whatever. If not, oh well, it's fine. Have a great day.